In this video lecture, we will go through the strength of hydrogen bonds and the effects of hydrogen bond, right? Mainly in the effects, we will look into some abnormal physical properties of substances due to the presence of hydrogen bond, right? This is the second video lecture on hydrogen bonding, right? For the detailed explanation of what is hydrogen bonding and how it gets formed, you can view the previous lecture, the first lecture on hydrogen bonding, right? So let's talk about the strength of hydrogen bonding. Before talking about the strength of hydrogen bonding, let's quickly look into what was hydrogen bonding, right? A quick recap. Hydrogen bonding is present in those molecules where you have hydrogen atom, right, linked to a highly electronegative atom, right, like this. Here hydrogen atom is linked to a highly electronegative element, fluorine, right, and due to electronegativity difference or due to high electronegativity of fluorine atom, right, this fluorine atom will attract the shared pair of electron towards itself, giving itself a slight negative charge, right, and hydrogen will get a slight positive charge, right. Now this electronegativity difference has resulted in the formation of a dipole, right. This is a dipole that has a positive pole, right, this positive hydrogen, right, and a negative end which is a fluorine atom, right. Now let's look how this dipole interacts with other hydrogen fluoride molecules, which are again dipoles, right. So here you have other hydrogen fluoride molecules, right. Here also you will have hydrogen fluoride molecules, right. So this is kind of a dipole-dipole interaction, right. This dipole, the positive end of this dipole, right, will interact with the negative end of this dipole, right, like this. Similarly, the negative end of this dipole, right, negative end of this dipole will interact with the positive end of this dipole, right. This is how the interaction we will show. So this interaction, right, we can say this interaction as a dipole-dipole interaction, right, or we also call it as an electrostatic interaction, because this interaction is between opposite charges, right, or this interaction is due to the presence of opposite charges between the dipole molecules or dipolar molecules, right. Now this interaction, right, this interaction or the electrostatic interaction between different dipolar molecules, right, will result in the formation of a hydrogen bond, right. This is a hydrogen bond, and this is a weak bond. If we talk about the strength of this bond, this is a weak bond, right. With the bond energy of hydrogen bond lies between 12 kilojoules per mole, right, to 14.8 kilojoules per mole, right. So you can see this is a very weak bond, and the bond's energy or the bond dissociation energy for a covalent molecule, for a covalent bond, is around 209 to 418 kilojoules per mole, right, whereas that of hydrogen bond, you can see it's 12 to 41.8 kilojoules per mole, right. So you can see the difference, right, you can see the difference between the strength of hydrogen bond, right, strength of hydrogen bond and the strength of covalent bond, right. So the strength of hydrogen bond, regarding the strength of hydrogen bond, we say that hydrogen bond is this is a hydrogen bond represented by dotted lines, right. This is a weak bond, right, but due to the presence of this weak bond, there are many abnormal properties of substances that can be explained. We'll see that in a minute, in a moment, right? So this explains us the bond energy, right, or the strength of hydrogen bond. Now, the strength of hydrogen bond actually depends on the electronegativity of the other atom, right, which is linked to hydrogen atom, right? So strength mainly depends on the electronegativity of atom linked to hydrogen atom, right? For example, in case of hydrogen fluoride, right, the bond dissociation energy is 41.8 kilojoules per mole, right? Whereas for oxygen, the bond dissociation energy is 29.3 kilojoules per mole, right? And that of bond dissociation energy, let's represent it with a dotted line. This shows a covalent bond, right? For that of nitrogen and hydrogen, it's 12.6 kilojoules per mole, right? So as I said, let's just correct this. Right, this should be, hydrogen bond is always shown with a dotted line like this, right? So you can see that since this fluorine has highest electronegativity, right? So bond dissociation energy is maximum, right? Bond dissociation energy is maximum in case of fluorine, right? If you come down, the electronegativity for oxygen is less, right, than fluorine, right? So bond dissociation energy also decreases, and that of nitrogen is further less than oxygen. So its bond dissociation energy, or the strength of hydrogen bond that gets formed between hydrogen and nitrogen, is further reduced to 12. It's reduced to 12.6 kilojoules per mole, right? So here the important point is that the strength of hydrogen bond depends on the electronegativity. It depends on the electronegativity of the atom linked to hydrogen atom, right? Now, although we said that this is a weaker bond, right? Hydrogen bond is a weaker bond, but this bond is stronger than weak van der Waals forces, right? This is stronger than weak van der Waals forces of attraction, but it is less stronger than covalent bond. So if you want to arrange it in order, hydrogen bond, right, is weaker than a covalent bond, right? Whereas van der Waals forces of attraction is lesser than your hydrogen bond, right? So just remember this order, right? As per this order, the strength of hydrogen bond is between weak van der Waals forces and covalent bond, right? Covalent bond we know is stronger than hydrogen bond, as shown from this bond dissociation energy. It's from 208 to 418 kilojoules per mole, whereas the bond dissociation energy of hydrogen bond is 12 to 41.8 kilojoules per mole. So you can easily see how weaker is hydrogen bond compared to this covalent bond, right? But this hydrogen bond is stronger than weak van der Waals forces of attraction, right? Now let's move to the other page. Now let's point out, since we just try to compare hydrogen bond and a covalent bond, let's quickly look into some point of differences between a hydrogen bond, right, between a hydrogen bond, right, and a covalent bond, right. We know that hydrogen bond is formed due to dipole-dipole interaction, right. This is formed due to dipole-dipole interaction, right. We have already discussed this. If you are still confused, you can watch the previous lecture. And covalent bond, we already know this is formed due to sharing of electrons, right. Covalent bond is formed due to sharing of electrons, right. And this bond, if you look at the formation, this bond is formed when a hydrogen atom is linked to a highly electronegative, when hydrogen atom is linked to a highly electronegative element, right. When hydrogen is linked to a electronegative atom, like nitrogen, oxygen, fluorine, right. Whereas if we talk about covalent bond gets formed, it gets formed between two electronegative atoms, which may be same or different, right. It is formed between two electronegative atoms, may be same or different, right. And we already discussed few minutes back that this is a weak bond, right, and this is a strong bond, sufficiently strong, right, compared to hydrogen bond, right. So these are some points of differences between hydrogen bond and a covalent bond, right. Now let's quickly look into the effects of hydrogen bond, right, because hydrogen bond effects of hydrogen bond, right, because this effect, the presence of hydrogen bonding, will help us to explain many abnormal physical properties, of substances. And what are these abnormal physical properties? It's melting point, boiling point, right, viscosity, surface tension, right, etc. So one thing we have discussed earlier, that hydrogen bonding, right, hydrogen bonding will cause association. It will cause association of molecules, right. Now due to this association of molecules, we have seen in the previous lecture there was one important effect, right, that we have seen in carboxylic acids, that acetic acid exists as a dimer, right. We know that due to this association, acetic acid, right, exists as a dimer, right, due to which if you see its molecular weight in benzene, its molecular weight will show as twice, right. Its molecular weight normally is 60, but in benzene you will see that its molecular weight will show 120, right. Why? Because here in benzene two molecules will associate. Two molecules of acetic acid will associate to form a dimer, right? And if you remember, I showed you this. Let's quickly see how it forms a dimer. Right, this is your acetic acid or any carboxylic acid. I've put the group R, any carboxylic acid. See, right, this is how we will draw it and show the presence of hydrogen bonding. Right, now this oxygen is negative, this oxygen is negative. Right, now we have in carboxylic acid this OH bond is polar, right? Since here hydrogen is linked to a highly electronegative element oxygen, or highly electronegative atom oxygen, so it will attract the shared pair of electron towards itself, right? Oxygen making it slightly negative and making this slightly positive, right? Similarly here, this is negative and this is positive, so here you will see the formation of hydrogen bond. Similarly, this is negative, so here you will see the formation of hydrogen bond, right? Let's show it with a different color. It will be easy to understand. This is the formation of hydrogen bond, right? So now we say that acetic acid will exist as dimers, right, in benzene due to the presence of hydrogen bonding, right? I hope this is clear. Now let's look into the other important properties of high melting point and boiling point, right? You have high melting point and boiling point, right? Due to the presence of hydrogen bonding, some substances like hydrogen fluoride water has abnormally high boiling points, right? So compounds having high hydrogen bonding show abnormally high melting and boiling points, right, due to the presence of hydrogen bonding, right? And the high melting points and boiling points of compounds, right, like compounds like high melting point and boiling point of compounds like water, ammonia, right, and HF, right, is due to the presence of hydrogen bonding. It's due to the presence of hydrogen bonding, right? So we know that if you compare these two, hydrogen fluoride and water, electronegativity of fluorine is highest, right? Since electronegativity of fluorine is highest, therefore the boiling point for HF should be higher compared to water, but we have found it exactly opposite, right? Boiling point of water is greater than the boiling point of HF, right? What could be the reason, right? If you look at the structure of water, you will see that each water molecule, right, is bonded to 4 other water molecules, or if you look at this is your let's look at the structure of water, right, to understand some of the properties, like why density of ice is lower than liquid water. Let's study the structure of water, right? So here you have oxygen, here again you have hydrogen, right? So this is electronegative, right? You have hydrogen bond here, right? Similarly, you have water, you have hydrogen bond here, right? And you have water here. You can see this is water molecule, right? So this will also form hydrogen bonds like this, right? And here you have again water. You have hydrogen bonding like this, right? So you can see that how water molecules are linked to one another, right? How water molecules are linked to one another, right? Each water molecule, if you will see, is linked to each oxygen molecule. If you look at this, each oxygen molecule is linked to 4 hydrogen atoms: 1, 2, 3 and 4, right? And so I'll just write it over here. Each oxygen, right, is linked to 4 hydrogen atoms, right? It is linked to 4 hydrogen atoms, due to which you will see this is kind of a cage like structure of solid ice, right? This is a cage like structure due to the presence of hydrogen bonding, right? This is a cage like structure that gets formed due to the presence of hydrogen bonding, and you have these empty spaces, right? You have these kind of empty spaces. This is an empty space, empty spaces, right? Due to this empty space, volume increases, right? Since volume is increasing due to the presence of this empty space, we know that density is mass per unit volume. So if volume will increase, density will decrease, right? Since density and volume, right, density and volume are inversely proportional to each other. Volume is increasing due to the presence of hydrogen bonding, and hydrogen bonding produces this cage like structure, right? This cage like structure, right? Due to this cage like structure, the volume increases, right? When volume increases, density decreases, right? This is a case in solid ice, right? This is how bonding takes place, or hydrogen bonding occurs in ice, right? Because we are trying to find out the reason why ice floats on water, right? When ice is floating on water, that means its density is less, right? So now it is clear why the density of ice is less. Because of the presence of this cage like structure, you have more empty spaces, right? You have more empty space due to the presence of cage like structure, due to which the density of ice decreases, right? So since density of ice is less, right, density decreases, therefore ice, we say, floats on water. This is the reason, right? And just remember one important thing, that each oxygen atom, this is an important point, that each oxygen atom is linked. Each oxygen atom is linked to 4 hydrogen atoms, right? Now we'll look at the structure of water in little more detail, right? Due to this linkage, due to this hydrogen bonding linkage, one abnormal property we have shown, that density of ice is more than water. Now there is a second abnormal property, high boiling point, and it's higher than hydrogen fluoride, right? Boiling point of water is higher than hydrogen fluoride, right? Although it should be less than hydrogen fluoride, right? Because the electronegativity of fluorine is high compared to oxygen, right? So normally the boiling point for water should be less compared to hydrogen fluoride. But in actual sense, in actual experiment or scenario, we see that we have noticed that the boiling point for hydrogen for water is higher compared to hydrogen fluoride, right? Now let's look into the reason why. If you I'll again draw the structure of water, right? This is because the structure of water will explain you the second abnormal property of boiling point as well, right? I said in the previous lecture that in the structure of water, due to the presence of hydrogen bonding, right, each water molecule is linked to 4 other water molecules, right? And these 4 other water molecules is surrounding a water molecule tetrahedrally, right? Let's just draw the tetrahedral structure. Just remember this point. Each water molecule is linked to 4 other water molecules, right? And earlier I showed you that how each water molecule is how each oxygen atom in water molecule is bonded to 4 hydrogen atoms, right? 2 hydrogen atoms are connected via covalent bonds and 2 hydrogen atoms are connected via hydrogen bond, right? Now let's draw the tetrahedral structure. Now here you have oxygen atom, right, which have a hydrogen bonding with hydrogen atom. Like this. Now here you have oxygen atom, let's right, and you have 4 water molecules surrounding this water molecule, which is shown in red, right? So this has hydrogen bonding like this, right? You can just notice that how one water molecule is connected to 4 other water molecules. Right, so this water molecule, you can see through hydrogen bonding, right, is surrounded by 4 water molecules, right? So this is kind of a tetrahedral structure. This is how it looks like, right? So in the previous slide that I was showing you, I showed that each oxygen atom is conjoined or is bonded to 4 hydrogen atoms, right? And due to this gave rise to a cage-like structure that has empty spaces, right? And due to the presence of this empty space, you have high volume is increased and density is decreased, right? And due to the presence of this kind of structure, where one water molecule is connected to 4 other water molecules, right? Due to this kind of structure, we say that the boiling point of water is higher than that of hydrogen fluoride, right? Why? Because if you see the structure of hydrogen fluoride is linked to one molecule of hydrogen fluoride is linked to two other molecules of hydrogen fluoride, right, like this. Similarly, this one is linked to one more hydrogen fluoride molecule, like this, right. So here one hydrogen fluoride molecule is linked to two hydrogen fluoride molecules, but in case of water, one water molecule is joined to four other water molecules due to the presence of hydrogen bonding, right. So due to which water has, this is one of the reasons that we can say that due to this water has higher boiling point compared to hydrogen fluoride. Although hydrogen fluoride, in case of hydrogen fluoride, the electronegativity of fluorine is higher, so the bond dissociation energy should be higher in case of fluorine, but so due to which the boiling point of hydrogen fluoride should be high. But what is observed is that the boiling point of water is higher. Why? Because water is connected to four other water molecules due to the presence of hydrogen bonding, right. So now we have understood two abnormal properties of water. One is why the density of ice is lower than that of water, and second is why boiling point of hydrogen fluoride is greater than that of hydrogen fluoride, right. And now let's look into some more properties. Let's look at it. It is said that the molecules that have hydrogen bonding, they have high volatility. They are less volatile. They have low volatility as compounds involving hydrogen bonding, right, between different molecules. They have higher boiling points, right. Since boiling points of compounds, right, is higher due to hydrogen bonding, right. Due to hydrogen bonding, boiling point is higher. So since boiling point is higher, we can say that volatility is the molecules that have high boiling point or have hydrogen bonding, they are less volatile, right. So they are molecules or compounds that have hydrogen bonding, they are less volatile, right, because molecules are strongly associated due to the presence of hydrogen bonding, right. Now what about viscosity? If we look at other physical property, viscosity and surface tension, right. Since the molecules are associated, since you have association due to hydrogen bonding, due to this association the viscosity is low, right. Viscosity is low, right, due to association. The substances which contain hydrogen bonding exist as associated molecules, right. So since they are associated, right, since you have association in compounds or molecules or substances that have hydrogen bonding, due to this association the volatility, due to this association the viscosity decreases, right. Due to association, viscosity decreases, right. It's difficult for them to flow, right, and they have high surface tension for the same reason, right. And for same reason, due to the presence of hydrogen bonding, right, ammonia has, if you look at boiling point, the boiling point of ammonia is greater than that of phosphine, right, because ammonia has hydrogen bonding. Due to the presence of hydrogen bonding, molecules are associated, they have, what we say is, in ammonia you have intermolecular hydrogen bonding. Due to intermolecular hydrogen bonding, molecules are associated. Since they are strongly associated, so they have high bond dissociation energy and they have high boiling points, and there is no such hydrogen bonding in phosphine molecule so it has less boiling point compared to ammonia. Similarly, if you look at ethanol, we know that ethanol has hydrogen bonding, right? So its boiling point is greater than that of diethyl ether, right? This is the formula for diethyl ether. On the same grounds that there is hydrogen bonding in ethanol, we say that its boiling point is higher than diethyl ether, because diethyl ether does not have hydrogen bonding, right? If you look at ethanol, C2H5OH, right? Similarly, OH, C2H5, right? This is your OH bond, due to which oxygen becomes negative, hydrogen becomes positive, this becomes negative, this becomes positive. You have hydrogen bonding, right? This is how you have hydrogen bonding between the molecules of ethanol, right? So I hope all this is clear, right? Just remember how the structure of water and ice looks like, right? And the cage-like structure of water starts collapsing when you start heating ice. When you heat ice, that cage-like structure dissociates, and when it dissociates, the hydrogen, and why it dissociates? Because of the dissociation of hydrogen bonds, right? So that is why hydrogen bonding is less, right, when you heat ice, right? So its cage-like structure dissociates, due to which volume increases and density also, due to which volume decreases and your density increases, right, for liquid water, right? So I hope all this is clear to you. Thanks.